Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight are three of our students who work at the Planetarium. I'll let them all say hi and introduce themselves, and we'll start with Rachel.
Hi, my name's Rachel. I'm a sophomore here at UMD, and I'm majoring in biology and minoring in environmental science.
Braden.
Hello, I'm Braden. I'm a music ed student here at UMD.
And I'm Eli. I'm a physics and astronomy student here at UMD.
All right, so it's exciting to have people back. I mean, not that I don't love doing shows just you and me, Eli, but it's nice to have other faces in here too. So tonight's show, I wanted to do one that we haven't done in, I want to say about a year, which is taking a look at planets outside of our solar system, planets around other stars. And I thought this could be a really good topic to talk about now, since the past few weeks, as we've been, fangirling over, or I've been fangirling over the James Webb Space Telescope. And one of the things we discussed that it could help us do is determine what other planets around other stars are like and whether there could even be signs of life. So I thought now is a really good time to kind of revisit this topic and take a look at exactly how we find planets around other stars, what we found, and what that means for our future of finding more Earths and more life out there. So as I get everything set up, as always, if you have any questions throughout the show, you can leave them down in the comments. Eli's going to will be keeping an eye on that for me. Will let me know if questions come up. There is a little bit of a delay between, when we see things and when things are said over the stream. So if we don't get to your question right away, it's either upcoming or we'll get to it at the end of the show. We'll have time to answer questions then as well. So let me get everything up and going. All right. So that should be up. So, as I said, we are taking a look at exoplanets, which are extrasolar planets or planets around other stars. And when it comes to searching for planets around other stars, the quick and easy version is it's extremely difficult. Planets are very small. They don't give off a lot of light compared to the stars that they orbit around, and they are incredibly far away. So trying to look for them and look for an individual planet itself to try and get a picture of a planet around another star is very difficult. So instead of looking directly for a planet, what we actually do is look for the effect the planet has on its star it's orbiting around. And that can give us indirect evidence that there is in fact a planet there. So there's kind of two ways that we can do this. The first way is looking for gravitational tugs that the planet is exerting on the star that it orbits around. Now, in order to understand how we do this, there's a couple of things we have to discuss, and one is an orbit. So you have probably heard, and we've said it here ourselves, the moon orbits around the Earth orbits around the sun. That's actually a very simplified version of what's happening, because for any two objects in orbit, they actually orbit around what's called the center of mass. And that's kind of like the balance point. So I know this is a very busy kind of screen right now, but if you focus on this kind of video here on the left, we have two objects. They are the same size, so they're the same, we're assuming they're the same mass, representing that by them being the same size, which means the balance point between them is going to be directly in between the two. And so when these things are orbiting, they're orbiting around that center of mass. They're both orbiting around that point halfway between the two of them. Now, if we take a look at the right, now we have a slightly different scenario where one object is more massive than the other. In that case, that center of mass sits closer to the more massive object. So it's sitting closer to this one. Now you can see that they're both still going around that point. They're both orbiting around that point. But the size of their orbits is different because of that. So this one isn't moving in as big of a circle as the smaller one. Now, if we keep going to more extreme scenarios where you have one that is a lot more massive than the other, that center of mass can actually lie inside of the other object. So on the left here, we have something that looks pretty similar to the Earth and Moon. That center of mass for the Earth and Moon lies inside of the Earth, which is why we can say the Moon orbits the Earth, because that's what it's doing as it's orbiting around this center of mass. But what we have to also take a look at here is the Earth is also moving. It's wobbling a little bit as it's also orbiting around that point. And then on the right, we have a more extreme scenario. This could be more like a planet around a star. Again, that center of mass is inside of the star because it's so much more massive than the planet. But because of that, the star itself wobbles a little bit. It moves because of that gravitational tug from the planet and because it's orbiting around that center of mass. And so when we look for planets around other stars, this is one of the things we look for. We look for a star that's wobbling, that's moving like this to indicate that there is a planet there in orbit. And so there is that center of mass situation going on. Now, actually detecting this wobble can be difficult because this is a very small motion. And depending on how long it takes the planet to orbit the star, it can be happening over years or even decades, which makes it difficult to detect. And so we don't actually look at pictures of the stars to watch them to see if they actually move in the picture. You can, but that's difficult to do and only works for the stars that are closest to us. So instead, what we do is we look at the light that we receive from the star. Because it turns out, if a star is moving, that affects the light that ends up reaching us. This is what we call Doppler shift. So if the star is moving, and I'll do it towards the camera, if the star is moving towards you, that light is going to get shifted blue to the blue end of the spectrum. And if the star is moving away from you, that light is going to get shifted to the red end. So if you have a star that's wobbling, then part of the time it's moving towards you, and so that light's going to get shifted to the blue, and part of the time it's moving away from you, so that light's going to get shifted to the red. So as it wobbles, as you watch that star's light, you're going to see the light shift back and forth, indicating that the star itself is moving and that it's wobbling. So this is one of the methods that we use to search for planets. We look at the light coming from a star, and we look for this shift back and forth in the light to indicate that the star is moving. And what's really cool, since this is determined by the orbit of the planet, that can tell us information on the orbit, that can tell us how far away the planet is from its star, how long it takes to complete an orbit around the star. But since what we're looking at is essentially gravity tugging on the star from the planet, that can also give us information on the mass of the planet and can tell us how massive it is, which is an important clue if we want to eventually figure out what the planet could possibly be made of. We need to know how much stuff is there. All right, so that is one method that we use, those gravitational tugs. And the other method that we use is called the transit method. And this is probably the most used method, although it does have its limitations. The idea with this is if you have a planet oriented just right, then as it's orbiting around its star, every so often, it will pass in between us and the star it's orbiting around, which will block some of the star's light. And for that little bit of time that it's in between us and the star, the total amount of the star's light is going to drop. It's going to become a little bit dimmer because part of the light is being blocked by this planet. And so what we do is we monitor the brightness of stars and we watch for those periodic dips in the brightness. Now, in order for this to be confirmed to be a planet, this has to happen at a regular time period. So like every 4 days, we see a dip in the star's brightness. That tells us that it's a regular patterned occurrence coming from an orbit and not just a random fluctuation, because stars do randomly fluctuate in their brightness. That happens. Now, this method, as I said, has its limitations because you can only find planets that happen to line up just right. So it's only telling you about the planets that are oriented just right to indicate themselves. But we've been able to find a lot of planets with this, and we'll get to that in a little bit. Now, one of the things that transits can tell us about is actually the size, the radius of the planet. Because the bigger the planet is, the more light is going to get blocked, and the bigger that dip in brightness is going to be. So we can find out how big a planet is. And if we know how big it is, and we're able to get that wobble information about the same star that can tell us the mass of the planet, those two things together can tell us if we have a large Jupiter-like planet or if we have a smaller Earth-like planet. And so we can get information on what the planet itself is like. All right, so we have had quite a few missions who have been dedicated just to looking for planets around other stars. Probably the most famous of that is the Kepler Space Telescope, which you're seeing here. It launched back in 2009 and was retired in 2018. So for 9 years, it spent watching the stars. And so its mission was to monitor the brightness of 150,000 stars every 30 minutes. So it took an image of 150,000 stars every 30 minutes and sent it back to Earth so that we could calculate how bright each of the stars was and see if that changed from picture to picture. As you can imagine, that is a lot of data. That's a lot of information. And we are still combing through all of the data that Kepler has sent back to us. So far, we have found over 2,600 planets around other stars with the Kepler Space Telescope, and we have several thousand more candidates. Now, what this means for it to be a candidate is we see some possibility, some like a good dip, but we're still looking through the data to make sure that it's a regular occurrence and not just one big random change. So lots of planets there found with Kepler. Now the current mission that is looking for exoplanets is TESS, the Transiting Exoplanet Survey Satellite. It launched back in 2018. And it has a much more ambitious mission than Kepler. It is aiming to take measurements of about 85% of the sky. That's an area 400 times bigger than what Kepler was monitoring. So it is looking at a much larger area. Since it is still relatively new, we still have all of the data that we're getting back, still waiting for confirmation on thousands of potential candidates. But we have found a few hundred at this point. I forgot to update this slide with where the number was at, but we're up to a few hundred confirmed planets with TESS. All right, so we have found thousands and thousands of planets around other stars. What you're seeing here is a map of where we have found planets around other stars up to the year 2019. So every star that's circled, we have found at least one planet around. You'll notice that there is a lot in this area here. That's the area that Kepler observed. And that's why there's so many in that area, because that's where Kepler stared at for, almost a decade. So based off of what we have found so far, we believe that at least half of all of the stars in the Milky Way have at least one planet. Now, there are about 200 billion stars in our galaxy, which means we're looking at probably at least 100 billion planets in just our galaxy alone. Now, looking at the planets that we found, we're starting to see kind of what types of planets are the most common. And so what we're seeing here is how many planets we have found in different kind of size ranges. We have Earths, super Earths, which are just a bit bigger than the Earth, Neptune size, Jupiter size, and then larger than Jupiter. Now, when we first started out, we were finding, changed slides on accident. When we were first starting out, we were finding a lot of these Jupiter-sized and larger planets. But it turns out we were finding those because those are the easiest to find. They're the biggest planets. They're going to have the biggest effect on the star they're orbiting around. So of course we're going to find those first. But now that we have spent decades searching for planets, we're actually finding that smaller planets are much more common than larger planets. And so we think small planets, like I just said, are more common, which kind of makes sense, right? You don't need as much material to make a small planet as you do a big planet. So it kind of makes sense that that would be the most common. But of course, they're also the most difficult to find, which is why it took us a while to find them, and why we think that these proportions are going to keep getting bigger and bigger, and these will end up, sorry about that, these will end up being the most common type of planet out there once we start finding even more of them. Now, as we have been looking at planets around other stars, we of course are excited to find any planet, but now that we have found thousands, we're kind of looking to fine-tune which ones we spend more time studying. In particular, we're interested in Earth-like planets. And by that, I mean a planet that is about the same size as the Earth, about the same mass as the Earth, so it's probably made of the same stuff, but also that it's the right distance from its star to be the same temperature as Earth, which would mean it could have liquid water on its surface. And the reason we are looking specifically for Earth-like planets is because we know Earth-like conditions are viable for life. Obviously, we're here. So we know an Earth-like planet can develop life, or at least it has at least once. So because we have that data point, that's what we want to look for. We want to look for more planets like ours to see how common they are and determine whether life was able to develop on those planets as well. And based off of what we found so far, and you can see some of the candidates here. These are, I think, some of the closest to us. Based off of what we found, we actually think that about 20% of the stars in our galaxy have an Earth-like planet, which again, 200 billion stars, That's, I'm going to completely mess up the math here, what, 40 billion Earth-like planets? Eli, correct me if I did that math wrong. I think I got that right. It's late. It's been a long day.
Yeah, I'm not going to try. I'll make a fool of myself.
Tens of billions. We'll just go with that. Tens of billions of Earth-like planets, which is both terrifying and exciting. And that's where part of my big excitement and astronomers' big excitement for James Webb is, because it's going to be the first chance that we have to really study those Earth-like planets, study the atmosphere of these planets, and look for signatures in the atmosphere that could indicate life. Things like a lot of oxygen. Because believe it or not, oxygen is not native to our atmosphere. We didn't start off having oxygen in our atmosphere. We have oxygen because photosynthetic plant life developed. And so finding an atmosphere with a lot of oxygen would be a very big indicator that there is photosynthetic life there, or some sort of life that is creating oxygen. And we'll get more into that next week. Next week, I'm going to do the searching for life and aliens show, and we'll talk more about those sort of indicators. But that's one of the many things that we're excited about. Okay. So to wrap up our show, I want to take a look at some of the planets that we have found, because there are, lots of planets that are similar to the ones we have in our solar system. We've also found a lot of really weird ones. So we're going to take a look at some of the ones that we have found. And we're going to start off with Kepler 186. So Kepler means it was discovered by the Kepler Space Telescope. 186 is just the catalog number of the star that was being monitored. And we're going to, in Kepler 186, we actually have 5 planets that are all pretty Earth-sized, but in particular, the furthest one out, Kepler 186f, is the closest to Earth-sized that we have found in the planet's habitable zone, in the region that gives it the same temperature as our Earth, so it has the potential to have liquid water on its surface. So this is the most like Earth planet so far that we have found, or at least since the last time I looked this up. This was the kind of most like Earth exoplanet. Now, another one I want to talk about is the exoplanet we found around Proxima Centauri. So Proxima Centauri is the closest star to us, and it turns out it has a planet. Not only does it have a planet, it has a planet that is potentially Earth-like, which is really exciting because Proxima Centauri is a little over 4 light years away, which is an incredibly large distance for us to try and travel now. But if we ever get to the point that we're able to travel, to the stars, this is the closest one we need to get to, and we could have a potential second Earth there. Which is kind of a good, I would say, step out in trying to colonize outside of our solar system. Now, we are still so far away from having the technology to make that happen, but it's nice knowing that we have a potential stepping stone very close by to us. All right, next up is Kepler 16b. It is about the same size and mass as the planet Saturn, so that maybe doesn't sound too interesting. But if you notice in this artist rendition, there's 2 stars really bright in the sky, right? We have the yellow one and the red one. Kepler 16b was the first planet that we discovered orbiting around a binary star system. So for those Star Wars fans, and Eli, correct me, is it Tatooine that has the twin stars?
Yes. Yep.
I'm learning, okay? That is a possibility, for real. Now, we have found planets around binary star systems. Okay, now getting into some of the more weird ones and extreme ones. Next is Kepler 10b. This was the first confirmed terrestrial planet outside of our solar system. So Earth, not Earth-like, but rocky planet. It's a little less than 4 times the mass of the Earth and about 1.5 times the size. So that was exciting, the first rocky planet found. But it is incredibly close to its star. It's about 1/20th the distance between the Sun and Mercury. So it sits 20 times closer to its Sun than Mercury is to our Sun. That leads to very extreme temperatures, with the daytime side reaching almost 3,000 degrees Fahrenheit, which means it's basically a perpetual lava ocean. But then the other side, the nighttime side, stays down to like negative 370 degrees Fahrenheit. So this is the most like two-faced planet with the most extreme conditions between day and night side. All right, Kepler 22b is a different type of planet than we have in our own solar system. This is what we think is a potential water world. So we think that it's a planet that is covered entirely in an ocean of water. Now, again, this is just based off of the little bit of information we have on like its mass and its size and its distance from its star. So things like James Webb are going to help us better understand what this planet is really like. But it's very cool, showing us a different type of planet than we have in our own solar system. All right. Believe it or not, Kepler 10b, our kind of lava world, or half lava world, is not the hottest exoplanet out there. That honor goes to KELT 9b. This is what we would call a super Jupiter. So it's about 3 times the mass of Jupiter. It is so close to its star that it makes a full orbit around its star in about a day and a half, which leads to temperatures on the planet exceeding 4,600 Kelvin, which is hotter than some stars, than the surface of some stars. And the reason we know it's so hot, not just because of how close it is to its star, but the little bit that we have been able to analyze the atmosphere, we see ionized metals, which is unheard of and only happens in the most extreme, hottest of conditions. Now, because the planet is so hot, it's very puffy. That atmosphere is very puffed up. And as you can see in this artist depiction, it's actually streaming away. It's being stripped away by that heat and being so close to the star. So this planet is not going to last forever. It is slowly being stripped away. But while it exists, it is the hottest planet that we have found. All right, so last 3, the first one we're going to talk about is not at all an interesting name. Excuse me, HD 189733b. This one is a little bit bigger than Jupiter. Also incredibly hot. It orbits its star in just over 2 days. The pretty blue color that you're seeing in this artist rendition is because it has liquid glass that is raining from the clouds because of how hot it is. It's so hot that it rains liquid glass. But it also has winds that blow at 5,400 miles per hour. So it's more of a sideways rain, and you would just get pelted by liquid glass traveling at 5,400 miles per hour. It's a very strange world. And last up, we have what I have deemed the Bejeweled worlds. 55 Cancri E is a super Earth that is believed to be covered in diamonds. And then HAT P7b is a super Jupiter where we believe it rains rubies and sapphires on the planet. And that is where we will wrap up our exploration of planets around other stars, at least for this week. Let me head back over to Zoom. All right. I always love doing the show. I love all the weird worlds. Like, it's great. We have lots of cool Earth-like planets, and we'll talk more about that next week when we do the alien show. But, like, a world that rains rubies and sapphires, or whose surface is covered in diamonds, like, it's so cool. All right. Let's see. Eli, did we have any questions?
No.
All right. Well, I will give it a minute, or a couple minutes in case there are any questions that do come in. Feel free to leave them down in the comments. I'm going to put you guys on the spot. Do any of you have a favorite planet around another star? Or any of the ones that we talked about tonight that you think are really cool?
The lava planet reminds me of Mustafar.
I was gonna say the lava planet.
I was
too.
also going to say the lava planet.
That sounds awesome.
What's really great about that one too, and I forgot to mention this, it's tidally locked. So the daytime side is always the daytime side, and the nighttime side is always the nighttime side. So it's just a perpetual half lava plain, half frozen barrenness. Yeah, it's bizarre.
So cool. That's so cool.
All right, well, let me tell you what's coming up, although I've already kind of talked a little bit about what's coming up. On Saturday, we are going to head back to our solar system and do a tour of the planets in our solar system. We'll get all up close and personal, talk about some of the really cool things that we have learned about them. And then I don't actually think I loaded the images up, so I'm just going to hop back over to Zoom. Next week, on Wednesday, we'll be doing the look at if there could be life out there, and kind of what we are looking for when we are searching for that. I talked a little bit about it today, but we'll go more in depth next week. And then next Saturday, I actually don't remember what we're doing, but I will tell you about that next time. It's been a long day. I forgot what our schedule is. Oh. All right, let's do one more check.
Does the glass planet weigh more and more because it is producing glass all the time?
So that's a very good question. No, because the glass is basically being pulled out of the gases in the atmosphere, just like the precipitation cycle here on Earth. The Earth doesn't weigh more because it rains, because that water was pulled out of the atmosphere. So it's all a part of the same system. But that is a very good question.
That's all we got.
All right. I'll give it just a second longer. And I guess we'll give a not great update on the planetarium. I won't say we, I made this decision. I made the very difficult decision to postpone reopening the planetarium as cases are getting very bad in our county. I want to do what I can to keep our community safe, so we will be postponing reopening for both public and private shows for a little bit longer until things are back down and back safe. It was a very, very difficult decision to make because we miss you guys. We miss having everyone in there. And I feel like I got a little taste of it and realized how much I missed it. And now, yeah. But we, in the meantime, are working on some fantastic stuff to have ready when we do reopen to bring you back in. We have some really great plans for when that happens. So until then, we will continue with our regular streaming schedule on Wednesdays and Saturdays at 7 p.m. Central. And as soon as I see that things are looking better and safer, we will announce our plans on reopening. So hopefully everyone understands. You can still hang out with us here, but we will get people in as soon as it's safe to do so. All right. Well, I think we will wrap it up there. Thank you everyone for joining us. We hope you have a wonderful rest of your evening, and we will see you next time. Bye everyone.